Sorry about that.
No worries, no worries. Alrighty, guys, I'm going to go ahead and get started. Presumably everyone grabbed some slides from up front here. As per usual, we've got a fair bit of work to get through. We'll see how far we get. If we don't cover everything, we'll just bring it back next time. The topic that we're essentially going to introduce today is the concept of relaxation, and importantly, how we add relaxation terms to the Bloch equations. We've got a little bit of makeup work, if you will, to finish out from the previous lecture, so I'll talk through a little bit of that material first, and then we'll get into this, some new considerations for the Bloch equations, if you will. So a little bit of class business. This is just, I like to offer at least a brief summary of where we were at the end of the last lecture. We described the so-called circularly polarized RF fields. These fields are chasing, if you will, the bulk magnetization at the Larmor frequency to push it down and affect a change in the orientation of the bulk magnetization. So we can bring it from, say, oriented along the z-axis and tip it down into the transverse plane, or tip it by any other angle if we want to. If we wanted to figure out what was the rotation operator that would confer the rotation that we wanted on our bulk magnetization, we came up with this, arguably somewhat clumsy transformation matrix that arose through this change of basis, a rotation by alpha, and then changing our basis back. And this compactly gives us what I'll call an RF pulse operator, something that we'll get some experience, we saw some examples, but we'll get some experience in using in MATLAB itself. And what's nice about this is you have this single matrix operator that affects a change on the bulk magnetization according to the flip angle that you want and according to the phase that you want. Now, it turns out for a lot of MR, the phase is not critically important. We'll talk about it some today, the phase of the transverse magnetization. And sometimes we'll leave it out, and then sometimes we'll bring it back in to talk about more specialized topics. What we did after that then was describe how we could actually design or choose the flip angle itself. And the flip angle really just arose from integrating the Larmor equation for the B1 field, right? So we're going to integrate the magnitude of this B1 envelope function as a function of time multiplied by the gyromagnetic ratio, and that will give us the total amount of flip angle. So the Larmor expression in its most basic form just says that the magnetization will precess. It's going to precess very, very, very quickly if it's a 1.5 Tesla field. It's going to precess quite a bit more slowly if it's a B1 field, because the B1 field is something like micro Tesla, whereas the B0 field, of course, is on the order of Tesla. We worked through then, at least in part, this idea of going from the laboratory to the rotating frame. The equation of motion for the bulk magnetization of the rotating frame without relaxation should be showing up right here, and I think I accidentally dropped it out. It looks like it's probably on the next slide. There it is. I'm not sure why I did that. At any rate, this looks very similar to the equation of motion for the bulk magnetization that we had in the laboratory frame, but we had to introduce this idea either of B effective or of this so-called fictitious field term. And so if you look at the B field that's acting on our spin system in the so-called rotating frame, it's the sum of two fields. This has units of field, but it's this so-called fictitious field that effectively demodulates the description of the bulk magnetization by the Larmor frequency. Again, we're just conceptually hopping on to the observational system at the Larmor frequency, so we're spinning with the spins. And this term effectively just offsets the conventional B0 field, if you will. The other field that we have to take into account, of course, is this B rot field. And this is the applied B field. So this might be your B1 field, and your B0 field. But it has to have the right coordinate system. It has to be described in the rotating frame. And then we saw some examples how this term here, the so-called fictitious field, offsets the B0 term, and then you're left with just a B1 description. And so the equation of motion for the bulk magnetization in the rotating frame, again, without relaxation, ended up giving us a system of differential equations that looked like this, which was pretty similar to the equation of motion for the bulk magnetization that we saw in the lab frame when we just had the B0 field. So there's mathematically a commonality there. And what we were starting to work on then was just a solution to this set of differential equations, because we noticed that the Y magnetization was coupled to the Z magnetization, and the time rate of change of the Z magnetization was coupled to the Y magnetization. So we've got some first order coupled differential equations. We know a little bit about how to deal with that because we did it once already, but I think that's what's going to take up the second part of our afternoon, or the first part of this lecture, rather. Sorry about things kind of popping in and out there. So this was the procedure that we went through for the simple case of free precession in the rotating frame. We said free precession in the rotating frame, of course, without relaxation still. We have to define our B effective. Our B effective always has this omega rho by gamma term plus this B field in the rotational frame. The only field that we care about when we're talking about free precession is just the B0 field. And so we add in the B0 field, and it looks a lot like B0 field in the lab frame, because the Z-axis or the K-axis in the lab frame and the Z-axis or the Z-prime axis and the K-prime axis and the rotating frame are just the same thing. And so it turns out that, and as sort of by design, this fictitious field here offsets the underlying B0 field here, so that the effective B field in the rotating frame is no field. And that hopefully makes a little bit of sense. We're trying to get rid of the effects of the B0 field in the rotating frame. So we're precessing with the spins, and consequently the spins don't appear to precess in the rotating frame because we're in that same coordinate system with the spins. So then we go back to our equation of motion in the rotating frame. We know what our B effective field is here. It's just the zero field. And we get the relatively uninteresting results after we use this determinant operator that just says the time rate of change of all of our magnetization components is just zero. And so free precession in the rotating frame isn't terribly interesting. It means that the spin has a state, and the bulk magnetization has a state, and it's just staying precisely in that state. There's no apparent precession because we're rotating with it, and it's not relaxing because we haven't added relaxation terms. It's just not changing as a function of time. So not a terrifically interesting case, but a relatively easy one to work through. What we then did is we wanted to look at the more interesting case of forced precession in the rotating frame, and still without relaxation. And so there we had to define our B effective field again, but our B effective field just used that circularly polarized field, and the circularly polarized field in the rotating frame just looks like a driving force along a single axis. It's just pushing the magnetization down, say, in a single direction. Because the B1 field in the rotating frame is just along a single direction, when we look at the system of equations that fall out of the determinant operator again, we get what we saw just a second ago, which is this system of coupled first-order differential equations. So our mx prime isn't really changing as a function of time, but our my prime and mz prime are changing as functions of time, and they're coupled to the other component of the magnetization. So the trick then was, how do we go from this system of differential equations to an actual solution for, say, a more interesting problem? And so that's the first thing that I'm going to do when I switch over to the camera. Questions about sort of where we are in terms of working with the equation of motion and the rotating frame? Okay. I tried to go back over that. Hopefully it's a little bit familiar from Friday, and then that gives you a little bit more traction. What we're going to do is start with this system of equations right now and work through a solution. It'll look a lot like what we had before for the free precession in the laboratory frame, but in this case it's forced precession in the rotating frame. Okay, so we really just want to talk about the solution to that system of equations. And we could begin by defining again what's our typical initial condition. And so we could take, for example, that mx prime initial condition is just, say, 0, and that our my prime, my prime, that's not very good, is it? Sorry. focus? Look okay? Because it autofocuses and then I can turn it off and it's not flipping around. Okay, sorry about that. It's okay? All right. So all I'm trying to do here is just define a plausible initial condition for our magnetization. And we choose the sort of not terribly interesting case of saying we have no transverse magnetization, but maybe we have some available bulk magnetization along the z-axis, which we conventionally call mz0. And that could, in fact, just be the thermal equilibrium value of the available bulk magnetization. Just if we're at perfect equilibrium, then our initial condition is just all of bulk magnetization pointing along z, and it has a magnitude m0. Now, that system of differential equations that I showed you before, we know some steps for sort of working through those, how we couple and decouple the equations. I won't work through that part again. When we're done sort of doing that decoupling of the equations, we can write down a general solution. And this will just look a little bit different than what we had previously because I want to be a little bit more specific about the B1 field. So here we're going to guess at a solution to this differential equation that says our my is a function of time, just looks like an a times a cosine, and it's the integral of gamma b1 e of t dt. And we'll see why this matters in just a second, but we want to use that integral form there because it captures sort of the effect of the B1 field or the B1 envelope function that we've chosen. That could be a step function, a rect function, if you will. It could be a sinc function. It could be anything else. And then we still guess that we maybe also have this so-called sine term on the other side here, and it's the same thing. It's integrating gamma B1 envelope function as a function of time. Let's see. The first thing we have to do in terms of trying to get at a solution for this is differentiate with respect to time. So I'm just going to say that dmy prime dt is equal to minus a gamma b1 e of t sine. So I just pulled out what was inside the integral, if you will, after I differentiate. Sine times still the same thing, the integral of gamma b1 e of t dt. And then we've got to do this for another term, and we've got our b coefficient still out in front, the everything that was inside the integral, which is gamma b1 e of t. And now this sine goes to a cosine after differentiating, and we're still integrating gamma b1 e of t dt. We can simplify this a little bit just by letting, here I'll write it on the side here. I'm going to go ahead, we did this, we defined this earlier, but we said our flip angle was in fact the integral of gamma b1 e of t dt. So I'll use that as shorthand now, and it will save me a little bit of space as I work forward. So all I'm going to do is make that substitution and say that my time rate of change is just minus a gamma b1 e of t sine alpha plus b gamma b1 e of t cosine alpha. If you remember back from our original equation of motion, we can make a substitution at this point and get us back to the mz component. So it was the last slide that I had up just a second ago, but we can make the substitution to say that, or to remember that our time rate of change of our y magnetization was also equal to gamma b1e of t times our mz prime. So that's just from the equation of motion. Using these two expressions together, we can just solve for mz. And we have that mz prime is equal to minus a sine alpha plus b cosine alpha. And remember, you've got this other term over here as well. So we're just dividing through by this gamma b1 of t term. We can look at some of our initial condition information to try to get a handle on these coefficients. So if we look at mz prime at time t equals 0, we also know that's the same as at time t equals 0, we also have alpha equals 0. Our initial condition is the magnetization is straight up. We haven't tipped at all yet, so alpha must also be 0. And as a consequence, we just recover beta. And we know that that has to be equal to our original initial condition, which was mz0. So that gives us a definition for B. We could go back to our my equation here and say that my prime of t equals 0 is equal to a cosine alpha plus b sine alpha. But recall that alpha equals 0 at time equal to 0. And so we just again recover that we have a, because sine of 0 is 0, cosine of 0 is 1. And per our initial condition, this has to be equal to 0. And so we just get a equals to 0. We don't have any initial y magnetization. That was the initial condition that we chose. Is that okay? So all that did was let us define now, say for this expression up here, keep the caps off. We know what our my as a function of time looks like now, because a was 0 and b was mz0. We have a relationship between our dmy dt and our mz prime. And so we can actually define our mz prime as well, because we know the solution for my of t. So I'm going to pull this sheet if that's okay. And we'll move to the next one. Take quarters up here. Okay, so having solved for A and B, we can define the magnetization's behavior as a function of time. We know that our mx component didn't change as a function of time, so it just has whatever its initial condition is, and under simple circumstances, maybe that's just 0. We can now use those A and B coefficients that we solve for to get our my as a function of time, substitute it back in because it was just a equals mz0, and we get mz0 times sine of the integral of our envelope function again. Sorry, I should write, say, a dummy variable tau d tau, and our mz prime of t is equal to we still inherit our initial condition, our mz0, and this time just times a cosine. Right? And it's just the integral again of our b1 envelope function. Now, importantly, maybe for a specific case, this solution is only maybe true for a specific time that we care about, and we call that time, say, 0 through time up to tau, say RF, the duration of the RF pulse. So the picture you could have in mind is our RF pulses, of course, are turned on and off for finite periods of time. And so I can have this be my B1 envelope function as a function of time. And it may be as simple as just a rect function. So it's just a box function that's turned on at time t equals 0, and it's turned off at time t equals tau r. Now, specifically, we didn't really maybe point it out very carefully yet, but at this point in time, our theta is equal to 0 degrees. This is the RF phase. Remember, when the RF phase was 0, we had our thumb pointing along the x-axis, and we were rotating the magnetization towards positive y. So we know that this is consistent with having chosen, say, the phase to actually be 0 all by itself. So we can look at a more specific example for the actual rect function like this. And if we want to be really clear about how we define that function, I'll just work with an example here. Then we let our B1 envelope function as a function of time be B1. And there's different ways of writing this, sorry. But we use some kind of box or box nomenclature to talk about the rect function that we have on the top right here. And the rect of t minus tau rf by 2 divided by tau rf. That's a definition for this function, and it just means that we have a magnitude of B1 for the time interval that we care about for 0 less than t less than or equal to tau rf, and it's 0 otherwise. This uses the same description that Lauterbur does in the Liang and Lauterbur book. So what we need to do is actually, you can see that this B1 envelope function shows up inside the integral, so we actually need to be able to integrate this function. Fortunately, it's not so bad. So the integral of our B1e of t function, let's see, I should make that tau. Tau from 0 to t, d tau is just the integral from 0 to t of the box function that we just wrote. You guys can probably write this as quickly as I can. Now, fortunately, those while the nomenclature is a little bit clumsy, or integrating this rect function over some interval, that boils down to just being the B1 amplitude times time, specifically for 0 is less than t is less than tau r. And so what that means is we can use this, the integral of that rect function, back into the system of equations that we had to finally define what those look like. And we get a final solution of mx prime of t is still equal to mx0, or 0. We had no initial x magnetization in the rotating frame. We have my prime of t is just going to take on that mz0 component times sine of gamma b1 times time. And so this means that when that B1 field is turned on, from time 0, we have no Y magnetization. But as time's increasing up through tau RF, we're going to be increasing the component of the Y magnetization. Let me just write one more line, and then I'll answer your question. The last thing that we can write then is the Z component of the magnetization, and that's just mz0. It takes on the cosine term and still looks like gamma b1 of t. And again, all of those, we've written it a few times, but this is specifically for 0 less than equal to t less than or equal to tau r.
Are we missing a gamma if you sine cosine?
Almost certainly. Yeah, I had them in my notes. I didn't transcribe it. So here, there's a gamma. Here, there's a gamma. It's a constant. It could be inside or outside the integrand. I just drew it outside because it fit a little bit more easily for me. Thank you. Okay, so these expressions here are interesting to talk about for just a second, right? This is basically saying in the rotating frame, if we're just observing what the bulk magnetization does, for this specific RF pulse that had zero phase, we're going to be increasing our Y component as a function of time and decreasing our Z component as a function of time, all the way up through a time that gives us an angle of, say, 90 degrees. Now, we said that we would only integrate up to some time tau RF, and that just becomes a design consideration for you guys. How far do you want your magnetization to go? Depends on the product of tau RF and the magnitude of the B field that you have turned on, right? So I can take my bulk magnetization and tip it down to the transverse plane. I can tip it down to be what we call inverted, or I can tip it 360 degrees. B1 will just continue to push on the bulk magnetization for as long as the RF pulse is active, okay? Now, what changes? I could design two 90-degree pulses with different B1s, right? I could have a small B1 and I could have a really large B1. What's the difference in what happens to my bulk magnetization if my B1 is larger?
It goes faster.
Goes faster. That's all, right? So I have a stronger B1. I'm going to push the magnetization down really quickly. We have limits on what our B1 can be because it's related to energy deposition per unit time, or the SAR, so we can't heat patients beyond certain limits. But the magnitude of the B1 field just tells you how fast you're pushing the magnetization. Sometimes we want to push it really quickly, sometimes we don't want to push it as fast, and there's a real art to designing RF pulses. Now, if you say you want a 90-degree pulse and you've chosen a large B1, what can you say about the duration of that pulse relative to a pulse that had the lower B1? Smaller, right? So if I'm pushing fast, I don't have to push for as long. And so we saw some examples of this, using this to calculate our alpha before, but those are some ways of thinking about what our bulk magnetization is doing as a consequence of those equations. Yeah. Okay, so that actually wraps up the section of the equation of motion for the bulk magnetization when we don't have relaxation. The thing to talk about next is what happens when we do have relaxation. Questions about sort of where we came from and where we got to? Okay. Questions have been good, both at the break and in the lecture, so just keep them coming. If we have time, I'll talk a little bit about this figure that's in the background here. This is one of these like terrific patent drawings, right? Absolutely terrifying piece of medical instrumentation, but one of the first MR systems that was built by a guy named Ray Damadian, who still, as far as I can tell, owns and runs a company called Phonar. If you're interested and we have time, I'll give you a little 5-minute MR history lecture at the very end that gives some background to that story. It's interesting. Anyway, so the guys that we'll talk about, at least in part today, are Felix here and Ed. They were awarded the 1952 Nobel Prize for the development of new methods for nuclear magnetic precision measurements and discoveries in connection therewith. Bloch was able to get his names on the equations themselves, and Ed Purcell has a fair number of other things sort of named after him. I probably said this when we took 205, but I think if there's ever a documentary film or a film at all made about MR, this will be played by George Clooney, and this will probably be Ed Harris. Anyway, so the Bloch equations with relaxation describe, or the equation of motion that describes the bulk magnetization's behavior, but we have to add some other terms. And in their in the laboratory frame, they take on this form. We've really just been working with these first terms here, right? Trying to understand just precessional field when we apply an external B field. The external B field we apply can be any B field, but we've specifically looked at B0 fields and B1 fields, right? What we have to do now is actually extend the Bloch equations to include relaxation. And relaxation enters in on the transverse components of the magnetization with a time constant called T2, or transverse relaxation. And it enters into the Z component of the magnetization primarily through T1, the longitudinal relaxation time constant. And you'll see later that the bulk magnetization is driven, if you will, to return to the equilibrium value of the magnetization, M0 or M0, if enough time elapses. We can, in fact, add additional terms here. This is a term that describes diffusion. I don't know if we'll have time in this course to talk very much about diffusion, but a really fascinating MR technique whereby you can label the phase of the of the spins, if you will, and actually recover pretty directly information about the diffusive behavior of the spins. So really one of the most kind of remarkable methods for measuring diffusivities, both in sort of chemistry samples as well as in vivo, and it's opened up a wide range of applications both in basic science and increasingly in research as well, wherein you can evaluate the orientation of fibers in different organs, whether it's the heart or the brain or the kidney or the livers. Really interesting. Anyway, what we have now is a relatively complicated situation. We've got a long differential equation. It's an ordinary coupled nonlinear differential equation. There's really no analytic solution, at least in general. We will, over the course of the next few weeks, work through some analytic solutions for simple cases, simple but important cases. And we'll also work up to understanding how we simulate these expressions in MATLAB. And that might sound daunting at first, but it's actually not so bad. And one of the most important things that you can learn to do as an MR scientist is to program Bloch equation simulations, which basically just allow you to set up the numerical methods for solving this set of differential equations in a way that you can keep track of what the bulk magnetization is doing in the presence of arbitrary gradients and RF pulses and anything, because that's really where all the fun happens when it comes to MR research, is designing the sequence of RF pulses and gradients that will give you the image contrast or the quantitative signal that you really want and is most useful. Now, interestingly, these equations are really just phenomenological, and that means that they match the data well, right? So that we can't really tie this all the way down to the quantum level, right? And our approximation of relaxation according to 1T2 and 1T1 is approximate. You'll see how there's some exponential behavior that drops out of all of this. This is really just an approximation. It's a good one. It works extremely well, but there's nothing derivable, if you will, about adding these relaxation terms. We just know them to be very consistent with experimental data. If we look at them closely, I labeled some of these already. This was in the lab frame. We have the first term is a precessional term. The second term governs the so-called transverse relaxation. The third term, the longitudinal relaxation. And this last term governs diffusion. We'll drop this term pretty soon and won't revisit it unless we have time at the very end of the lecture. We know what the precessional term does. It just tells us that the magnitude of our bulk magnetization is actually unchanged. But it's going to change its phase, or it's going to be rotating due to some externally applied B field. When it comes to relaxation, and we'll talk a fair bit about T1 and T2 relaxation and what they really mean, for now, just think of them as time constants. And if you're thinking about time constants, you should be thinking about exponential decays or exponential recoveries. We'll talk about the sort of the physics of T1 and T2 a little later in the lecture. What's interesting about relaxation is while precession implies that the magnitude of the bulk magnetization is unchanged, these other terms can have some interesting effects in that you can actually cause the magnitude of your bulk magnetization to be zero, for example. And that's a really useful thing when we're generating image contrast, because we can actually make certain tissue types to be very, very dark. We call it nulling. So we can null a particular tissue that has a particular T1. And when it comes to image contrast, it's really nice if you can make something really, really dark, because then it tells you what that tissue was. You say, oh, well, that got really, really dark. We timed our sequence such that, things like fat would be really dark, so that worked, and that tissue over there is probably fatty, and fat's usually pretty benign, so the patient can go home, no problem. Things like that. So it really becomes in principle, a very useful technique to manipulate the contrast of the images by manipulating the bulk magnetization. This is the process that we're going to work on describing. We've got a set of spins here that are being excited. They're excited by 90 degrees in precessing. But over time, after the RF pulse stops, things will rotate back to their initial condition again. So just showing that one more time. Things are going to be precessing and be excited simultaneously by about 90 degrees. And then the RF pulse is turned off. Things they'll continue precessing, but they'll slowly relax back to that equilibrium state. And so the magnetization relaxes after excitation, and excitation is that process of forced precession, if you will. The underlying free precession is sort of always there. It's only apparent in the laboratory frame. If we switch over to the rotating frame, then that precessional behavior is not obvious to us because we're precessing with the spins. In the rotating frame, the equations take a slightly different form, but have some terms that are hopefully familiar from the last lecture and the little introduction I gave today. We basically have this precessional term here still, but it uses the B effective field, which includes that so-called fictitious field, and the B field as described in the rotating frame, so that we can effectively get rid of the B0 field and then just look at the effects of, say, the B1 field in principle. And we still have very similar transverse relaxation and longitudinal relaxation terms. Remember that K and K prime axes are equal, and so these terms end up looking very similar to what we had before. So the thing we want to talk about then is how we introduce relaxation into our equation of motion. And we'll talk first about free precession in the rotating frame when we add relaxation. We know this was the Bloch equations in the rotating frame. We have these relaxation terms added. We know from what we had before, when we're talking about free precession, our B rot field here, does it pop up? Yeah, sorry, I don't know why it's on delay like that. We need to make a substitution for actual B effective field under the conditions of free precession, right? Free precession just meant that our B rotational field was just B0K. Our K axis, again, shared in the two coordinate systems. And our omega rot is just minus gamma B0K. And that means that these two terms offset each other for the specific condition of free precession, because that means we're only applying the so-called B0 field. So not a terribly interesting case. It just means our B effective field, the effectively applied B field in the rotating frame, is just the zero frame. And that causes this precessional term to drop out, okay? Because this is a zero term, we're just going to lose any components that would enter it through this precessional cross product, if you will. So that leads us to a different set of differential equations that we have to work with and solve. When we drop that precessional term off the front, obviously there's no more precession. We still have T1 and T2 relaxation. We went ahead and dropped the diffusion term because we're not going to talk about it for a while. And we're left with a system of first order linear separable ODEs. They're homogeneous in X and Y. I'll show you what that means in just a second. But when we work with differential equations, we oftentimes have like a term that's a derivative term, and then the first order term, or the zeroth order term rather. And then if it's equal to zero, we call that a homogeneous differential equation. And if it's not equal to zero, we call that an inhomogeneous differential expression. Here, because of this M0 term here, the description of our Z magnetization is described by an inhomogeneous differential equation, whereas the X and Y's, because there's no sort of constant term that shows up here, they're described by so-called homogeneous differential equations. Hopefully those are terms that are familiar. It's not critical. What we're going to do in just a second is work through, again, some solutions to some differential equations. And then we're going to talk about, what do we actually really care about in this class. All these examples are useful for understanding how the spin system behaves and performs. But of the many different examples we've worked through, we only actually care about a couple of them for understanding MR imaging and image contrast and so forth. Something that'll be useful, this will come up in a page or two. I'm going to flip over to the document camera in a second, will be Euler's equation. And it's just a way, it's a way of using complex exponentiation to describe vector quantities. So a lot of times we'll talk about just the transverse magnetization. We don't necessarily care if it's the x component or the y component. We just want to know how much transverse magnetization is there. And it turns out to be mathematically convenient if you combine your x and y components of your magnetization into a complex vector that's represented using Euler's notation. And so here we have a bulk magnetization vector, just the transverse magnetization. And in principle, it has a real x component, the mx component, and we can mathematically say it has an imaginary my component. I put this diagram here for now. You guys can kind of refer back to it when you need to. It'll pop up when we get into combining our mx and my terms into a single just transverse magnetization term. For most of MR, we don't care too much about what the phase of the magnetization is. Magnetization could point anywhere, but it's also zipping around at 64 megahertz relative to our coil. Mostly what we care about is what's the magnitude of our transverse magnetization. And so we lump these two terms together for the most part in most of MR, and I'll show you how we go about doing that in a second. So our task right now, just going back a slide, going to this slide, is talking about solutions to this set of differential equations. We don't have to worry about precession, we just have to worry about relaxation, and that'll enter in as a bunch of exponential functions. Questions about what our plan is? Okay. Let me look at my notes quickly. Yeah, we'll work through probably this first part and then maybe take a break. If you look at that equation of motion that I wrote down with relaxation just a second ago, you'll see that we can sort of identify the individual terms, if you will. And so let's write a vector for the bulk magnetization, that first column, which is just the time rate of change of our x component, our y component, and our z component. I'm writing this as a column vector. So just those three components. This is coming out of that equation that was just before the Euler equation slide. This is just a column vector. And if we look at what components we actually had in that sort of longer expression, we had only one component along the I hat direction, and that looked like m minus mx prime divided by t2. We only had one term along the j direction, and that looked like minus my prime by t2. And we only had one term along the k direction, and that looked like minus of mz prime minus m0 by t1. And so this is just making more explicit the system of differential equations that was described a second ago. So now we can talk about how do we actually get at solutions of these things, depending on how recently or not you took a ODE course. We'll just look at this first expression first. These are all, fortunately, they're already separated, right? So mx only depends on mx. The time rate of change of my only depends on my, and the time rate of change of mz only depends on mz. So that's useful or simplifies things a bit. So the first thing is just that first expression, dmx prime dt, and that's equal to minus mx prime by t2. Lots of different ways to go about coming up with solutions to differential equations. You might have your own favorite way of doing this. The first thing I'm going to do is separate the variables. And that's simple enough. I just want to get my mx's all on one side. So I'm going to have dmx prime divided by mx prime. And that's equal to minus dt by t2. The next thing I'll do is integrate both sides. So integrating the left-hand side, I just get the log of the absolute value of mx prime. And that's going to be equal to minus t over t2 plus some constant. I can then exponentiate both sides. And I just get the magnitude of mx prime is equal to e to the minus t over t2 times e to the c. We'll just call that, we'll just make that a new constant. This e to the c is a constant, so we'll just put it out front as an a. So we have a times e to the minus t over t2. And oftentimes, at least at this point, we're just talking about time being positive. There's different ways to sort of describe it, but we'll just say that that is, in fact, the solution to mx as a function of time. We don't worry about the absolute value because we're just talking about positive times anyway. So by extension, then, hopefully you could work through the exact same thing for my prime of time. We'll give it a different leading coefficient because we'll solve for that in just a second. But we end up with two expressions like this for the components of our transverse magnetization. So what does that say about the transverse magnetization? It just means that as soon as you create it, as soon as you have any mx or my magnetization, it's unstable and it wants to decay. It's going to be governed by a decaying exponential that in itself depends on T2. And the T2 will be species specific. We'll get into T2s and T1s a little bit later. This is just the mathematics of it. Looking at the, sort of our most simple general case, then we say that mx prime at t equals to 0 is equal to a. We know that from the last two expressions I wrote. And we usually just say, well, that's just our initial magnetization that we have available. We do the same thing for my prime as a function of time at time t equals to 0, and we just recover b, and we know that that's just also our initial condition. And so at the end of the day, then we just have two expressions for the transverse components of the magnetization that depend on those initial conditions and indicate that the initial condition is not stable and just decays as a function of time. So that's one general solution. We have to know what is our initial condition, and then if we're just observing the spin system at that point in time, nothing else is acting on it as a function of time, it's just going to decay and go away. Remember the problem that we started with was the free precession in the rotating frame. We've just added relaxation now. When we looked at this without relaxation, we didn't recover this exponential term, and it just meant that your initial condition was stable. It wasn't a sort of a real circumstance, if you will, but mathematically it would bear out that your bulk magnetization would just keep doing the same thing, all day, every day. It's only when you add relaxation, of course, that these things decay. The last slide that I showed you was Euler's notation, complex notation for vector variables, if you will. And so oftentimes in MR, we just want to define the MXY magnetization. It's a vector quantity because it has components in the X and Y plane. And I just want to show that this can be mathematically taken as the sum of the other two components, which is just mx prime of t plus I times my prime of t. This is a definition. I guess I should write it as a definition. We know what those individual components actually look like because we just recovered them a second ago. And so we know that this is mx0 e to the minus t by t2 plus I y0 e to the minus t over t2. And we just take these two terms together now here and call them the initial condition for our transverse magnetization. We don't really talk about the X and Y magnetization anymore. We just talk about the transverse magnetization. It's still governed to decay, of course, by e to the minus t over t2. And we could, in fact, add a phase term in here. It's not always important for MR. Sometimes we want to keep track of it. So I'll just write it in red here as a term that, depending on exactly what we're doing, sometimes we care if our magnetization is pointing along a particular direction. We'll get into so-called phase contrast techniques where we're differencing things and the phase is meaningful. For a lot of MR, the phase is not terribly important. And so from that expression, this expression here just gives us the so-called transverse magnetization. And we can recognize that the magnitude of mxy of time is just equal to mx0 squared plus my0 squared square root. And that the initial phase, if you will, sorry, I wrote this wrong. This is the description of the initial condition. This is just mx, y, 0. Obviously, it's decaying as a function of time, so I couldn't have written what I wrote. Then we can talk about what's our initial phase. And our initial phase just depends on the components of magnetization that you have. Usually use the arctan2 operator, and it's my0, x. So what's important here is really just this statement, because we want to come up with sort of an increasingly compact way of talking about the magnetization. And in truth, we don't really care about mx or my. We just care about the transverse magnetization. And this defines the transverse magnetization for us. And importantly, it just says that the transverse magnetization just decays as a function of T2. As we're describing it, only depends on T2. Okay. If there's questions, now's a good time. Let me know. You can come up front or just reach up right now. Otherwise, let's take a 5-minute break and come back just like a minute after 2. Question in the back?
Is there a reason we're not doing a definite integral from 0 to tau r?
Are you looking at this slide?
On the left side.
We don't have to treat it as a definite integral when we're just thinking of what's the behavior of the transverse magnetization for like just all time. We're not if we wanted to figure out what was the transverse magnetization at, say, a specific time, then we could define the limits of the integral and say, oh, it points over here and it has a certain length because it's decayed. But this expression here gives us a general solution to mxy as a function of time. Okay, let's take a 5-minute break and come back in a few minutes. Yeah. Yeah.
Student of chemistry department.
Okay.
I want to, when I left, I want to take this course.
Oh, sure. That's fine. Yeah, of course, of course.
Can I participate in labs?
Yeah. It might. I'll let you know. It'll depend a little bit because it's a big class and it gets a little tricky. Maybe.
Okay, but I think there is no regular lab, like there are lectures only Monday and Wednesday, 1 to 2 p.m.
Yeah, occasionally on Friday.
Yeah, on Friday, actually I am not registered because on Friday I cannot, like I have classes in my
Okay.
department.
Yeah.
So
Yeah.
I can only attend 1 to 2 p.m. but not 2 to 3.
Yeah. No, it's okay. I mean, the lectures are recorded. Everything's put online with the slides. So if you miss something, hopefully that's a good way to get access to the materials as well.
Okay, and the last week actually I mean the last week I just
Yeah.
that I went to India and I came back in last week, so I cannot attend the first week class, but I have seen the online lecture.
Yeah, it's all public, so I mean, as long as you know where to find it, it's public.
Okay, and it would be very helpful for me if I can participate in the lab.
Yeah, that's the only part I can't promise because we have a lot of students and we don't have that many. We go to the clinical MRI systems and we just only have space for so many people. So I'm pretty flexible. I'll work with you. I just can't promise it.
Okay.
Yeah.
Okay. But that is mean that no lab now, like this week.
No. The first lab is the end of the month, 24th, 25th, something like that. So
And the time will be like a Friday afternoon?
No, I forget. I think it's a Monday and a Wednesday, and they're at night because that's when we can get on. So they're in the window of like 6 to 9 p.m. Yeah. Hopefully.
Okay, thank you very much.
This one will summarize the alpha. Yeah, that's what yeah, last time we just said yeah. And then you actually like understand what you're writing rather than like because I know so what I was saying I spent like an entire day. So the first 15 papers were pretty much on regression and research. So like the first paper, I kind of like started with 205. I did, and it's just gone more and more. It was, yeah.
Alrighty, guys. I'm gonna go ahead and get started again. What we worked on was we were talking about forced precession and the rotating frame with relaxation. That's a lot of words. Hopefully you know what each of those terms mean. We only worked through the solution for what happens to the mx and my components of the magnetization. We didn't talk at all about what happens to mz. I'm debating a little bit sort of how much of this to show mathematically, but I think I'll at least set up the problem. And then I'll probably put my notes up there so that there's like a screen grab of it, and we may not go through the whole thing. We'll see. Question for you guys though: how's this working for you when I'm working here and you're seeing me write up on the board? Is it effective? Are you able to like see what I'm writing? Am I going too fast? Too slow? Okay, that's surprising. I expected one or the other, but not sort of right in between. Okay, I'm going to keep going sort of as planned then, and keep working through some things. And it won't be every lecture that we actually work quite this extensively on the board, but this is one of them where we have one of the lectures where we have a fair bit of material to get through. So I'm going to switch back over. The thing we have to talk about is what's happening to our MZ magnetization. That was the component we didn't get to yet. Still under the same conditions, still free precession in the rotating frame. Okay, so if you go back to those system of equations that we had, we can isolate just the mz component. And what we had was that the time rate of change of the mz component was equal to, I have to be careful here because there's some minus signs. I'm going to pull the minus sign up into the expression now. The minus sign was in front as originally written, and that means that we have a minus, which gives us a positive M0 term, all divided by T1. So again, we've got a differential equation here. This happens to be an inhomogeneous first order differential equation. We're going to rearrange it a little bit just so I can see terms a little bit more clearly and write it as mz prime dt. I'm just going to carry over the mz term. So I have mz prime by T1. And this is equal to M0 by T. So that was just rearranging. And it's this term on the right-hand side here that means we have what's called an inhomogeneous differential equation. And that creates a little bit of complexity for us, but it's not too terrible. When it comes to trying to find solutions for these things, of course, there's a lot of ways to go about doing this. If you've taken an ODE class, you've probably taken it more recently than me. At any rate, we can identify this term on the right-hand side as being the derivative term, the time rate of change term in this case. This term in the middle here we could write as being depending on some p of t times x. For us, p of t is going to be very, very simple. This is the solution I'm writing is general enough that this could actually be some function of time, but for us, p of t is just 1 over t1. We'll talk about that more in just a second. And then this right-hand side here, the inhomogeneous part could in fact also be a function of time. And the solution to these kinds of differential equations can get really complicated when these things are all in and of themselves functions of time. What we're interested in recovering is, say, our mz is a function of time. As I've written it here, the solution is going to take the form of x of t equal to 1 over u of t times the integral of u of t times q of t dt plus a constant. And importantly, we didn't define it yet, but u of t is this what we call an integrating factor, and it's equal to e raised to the integral of p of t. we call this thing here, this is called an integrating factor. Try to fix my paper here so. Okay, so let's go ahead and define a couple things. The first thing we want to do is work on this u of t. So let's start trying to figure out what's u of t. We have that p of t, fortunately for us, is pretty simple. I said it a second ago, but it's just 1 over t1. And so u of t is just that function exponentiated and integrated. So it's the e to the integral of 1 over t1 dt. And we can solve that integral hopefully pretty easily, and we just have e to the t over t1. So we know what our u of t function is, the so-called integrating factor. And now we can get back at trying to work at the actual solution that we had here a second ago, because we know u of t, we know q of t, and that's everything we need to know because we had p of t to give us u of t in the first place. So what we have then is mz prime. So this is bunching up a little bit. Mz prime is a function of t, just coming from this expression here. So we can write this as e to the minus t over t1, and that's our 1 over u of t term. And that multiplies onto the integral of e to the t over t1, which was our u of t. Times, better be a times, right? Yeah. Times m0 over t1 dt plus some constant, close up my brackets. And that second term here, this is the so-called q of t, as I had in that general expression a little while ago. We need to sort of just work through a little bit of algebra to boil this down to something useful. Let's leave the e to the minus t over t1 in front. We'll pull the m0 out in front here and just see this as e to the 1, the integral of 1 over t1 e to the t over t1 dt. Still plus a constant. So that was just rearranging some terms to keep my head on straight. Still carry through with this e to the minus t over t1 term in front. Now I have to work out the solution to this integral here. Hopefully we recognize solutions to exponential functions, and we just get e to the t over t1 plus some constant, I'll call it c prime, and we still have this last constant c. I'm just going to multiply through now with this e to the minus t over t1 term. And in front here, I'll get an m0 term. The second term here will be a plus m0 c prime e to the minus t over t1. And then the last term will be a plus c e to the minus t. There was a cancellation of two exponential terms for that very first term. We see we have a common m0 in both of these. Let's pull that out in front. And we just have m0 times 1 plus c prime e to the minus t over t1 plus c e plus t. If you work through what we know about our initial conditions, we can find that C1 is actually equal to minus 1. And we can solve that C is actually equal to our initial condition, mz0. Both of those coefficients are required to satisfy what happens at, say, time equals 0 and time equals infinity. So I'll just say So this is nice. We actually got all the way through to a final form of the solution for our MZ prime magnetization. And it just works out to be MZ prime of T is M0, 1 minus E to the minus T over T1 plus MZ0 E to the minus T. We've got two sort of essential terms that we ended up with here. One that's related to the equilibrium value of the magnetization, and one that's related to our initial condition. And so this first term here, what it represents is the return to equilibrium. So if you look at that function, as time goes to infinity, what's e to the minus infinity? Just 0. And so we're just left with an m0 times 1 term, so m0. And this term goes to 0 if time goes to infinity. And then this term here is just representative. It basically says that there's the decay of what we call prepared magnetization. So looking at this term here, we can see it obviously has an exponential decay term. What's decaying is the initial condition. The initial condition is some prepared magnetization. We forced the system to have a particular state, probably because we applied a B1 field, and now has that state. What happens as the magnetization returns to its equilibrium state? This term is going to decay. It's the decay of that initial condition, and it's going to, the magnetization is also going to be recovering back towards its equilibrium value of magnetization. So if we look at, I'll just write it explicitly here, if we look at mz prime of t equal to infinity, we just recover m0. If we look at mz prime of t equals to 0, we just recover the initial condition. So now we've got a set of equations that are really useful for us, and in fact that's the next thing I'll talk about, is all these different examples that we've worked through, which are the ones that we actually really care about. And this solution for both the transverse and longitudinal magnetization are really central to understanding image contrast in MR. And so we'll spend a fair bit of time talking about those, working with rather those sort of exponential functions. The last thing, I'll just set up the one more problem. We won't work through the solution because we'll see how complicated it forms. But what circumstance have we not talked about yet? We were just talking about free precession in the rotating frame with relaxation, so we still have to talk about what? Force precession, right? So let's do that relatively quickly. I just want to set it up so you guys see what it looks like. We won't work through the actual solution because there isn't one. Okay, so sounds like most of you sort of were on top of it when I said it, but this will be for forced precession in the rotating frame with relaxation. And again, I'm just going to set it up, and then we'll see where things kind of land. Remember, we had our dm rot by dt, and that was equal to this precessional term still. So we still had our unit vectors. These should all be in the rotating frame I hat, I prime, j prime, and k prime. Our bulk magnetization vector was just described by mx prime, my prime, and mz prime. And now we're talking about forced precession. And so the B effective field that we end up with is just, say, gamma B1 E of t. Now, that and that alone we already looked at, right? This was, as written right now, just without relaxation. What we also have to include, though, is what happens to mx prime and my prime because of relaxation, and what happens to mz prime because of relaxation. We can write out the individual time rate of change components, and we just have dmx prime dt equals, what do we get from the precessional term here? Yep. Then what do we get from the relaxation terms? What do I incorporate from over here? Anything? I still have this x prime term over here, right? So I still have a minus, I probably shouldn't have written a plus, a minus mx prime by t2. Okay, well, we just worked through that. We know how to solve that. Let's see what happens next. We've got dmy prime dt is equal to anything from the precessional term. So remember, I have to take the determinant of this thing. When I look at my j direction, I get an mx prime times 0, so nothing there. And then I have a gamma b1 term times my mz term here. So I should get a gamma b1 envelope of time times mz prime. So that comes out of the precessional term. And then do I have anything over here that's related to time rates of change of my? Or anything that's along my j-axis, if you will. And that's my my component, right? So I still have a minus my prime by t2. All I'm doing is following through on this determinant operator for each of the components of my magnetization, and then including the relevant term along the particular direction that accords with the relaxation. So then here, dmz dt, that's just equal to minus gamma b1e of t mz prime. That comes out of my k direction here. I have mx prime times 0 minus gamma b1 e of t times my prime. So that's this term. Oh, I should, yeah, sorry, there should be a y. Scratch that up. So this is the precessional term that comes out of the determinant. And now I look over here, and I still have to add the relevant mz term, and I have something like minus mz prime minus m0 over t1. This little minus sign can be a little tricky, right? Because the minus sign is in front of the fraction. Depending on how you carry through with your algebra, sometimes you bring it up and in, and then change the sign at the m0 term. The point here is just that we have a relatively complicated set of differential equations. Again, not impossible to solve for certain circumstances, but hard to solve for many circumstances. Things are coupled between our my and mz direction for the simple case of having an RF pulse phased only about the x-axis. And you can see that the time rate of change of my depends on mz and my, and the time rate of change of mz depends on my and also mz. So the general solutions to this don't exist. We can talk about really specific solutions, and that's in fact mostly what we'll do in this class, is use some very specific circumstances to understand how this gives rise to everything from echoes, which are the fundamental MR signal, to governing image contrast, which of course is important for coming up with a useful diagnostic MR image. So the point here was just to show that we could come up with a set of differential equations to solve, but solutions to this are really hard. And we're not going to do anything analytically with this particular set of equations. We'll work with some other circumstances. And I'll tell you in just a second why making consideration for relaxation during forced precession isn't terribly important to us. Does anyone have a thought about that? Yeah. So there are very different time scales typically, right? Forced precession is quite quick. We're using millisecond RF pulses to tip our magnetization over very quickly. And on those short time scales, relaxation oftentimes doesn't matter. Relaxation is happening on hundreds of milliseconds or millisecond time scale. So oftentimes we can basically ignore the effects of relaxation when we're forcing the magnetization to do something. And so a lot of what we'll work through over the next couple lectures is going back and forth between periods of free precession when the magnetization is just returning to its equilibrium state and we may be trying to detect the signal, and periods of forced precession when we're pushing on the magnetization with the B1 field and making it do something that will govern the underlying image contrast. Let's see if I can get out of my seat here. So this was the example that we just worked through, was forced precession in the rotating frame with relaxation. Again, because RF pulses are short and the relaxation time constants are long, generally this isn't a circumstance that directly concerns us. Your homework will probably link into this concept though. There is some complicated coupling that's involved there. We can, of course, simulate this. Those equations actually aren't that hard to simulate. You guys will each build your own Bloch equation simulator from some of the components that we've talked about so far. So it's something that we can do relatively easily, as it turns out. So we don't need the analytic solutions. So at this point in the class, we've covered a lot of different sort of examples of solving all these differential equations. We've considered all combinations of both free and forced precession, with and without relaxation, and in the laboratory in the rotating frame. So there's 8 central examples that we sort of worked through to different extents. Sometimes we said, it gets too hard, we'll just leave it there. But for 6 of the 8, we basically worked through it with some at least simple examples. Which ones really concern us in 219? Well, I alluded to this a second ago. We care a lot about free precession in the rotating frame with relaxation. So and we care about forced precession in the rotating frame without relaxation. So you'll notice that what we really care about mostly is the rotating frame. Sorry. If I don't fix it now, it'll be there next year too. So what we really care about is what's happening in the rotating frame. So that's nice. It sort of knocks out half of the examples that we worked through. We care about free and forced precession, but we care about them on very different time scales. We care about free precession typically over several milliseconds or maybe even seconds, and consequently relaxation plays a critical sort of role there. When we're forcing the bulk magnetization to do something with so-called forced precession, we still care about it in the rotating frame, but we don't generally care about the effects of relaxation because these time scales are so different. And what we'll see is we are going to keep track of the magnetization. We start working with pulse sequence diagrams. They describe the sequence of events that manipulate the bulk magnetization to produce a certain image contrast. We're going to keep track of the magnetization during periods of free precession as well as periods of forced precession, both in the rotating frame, but we only sometimes care about the effects of relaxation. And we can simulate them all. So what I want to do over the next, call it 30 minutes or 25 minutes is just talk a little bit about the sort of what is this T1 relaxation and what is T2 relaxation. If I don't get to everything, it's not terrible. It's both somewhat in the books and then of course the slides as well. The thing to remember about T1 and T2 is that it's tissue specific, meaning that different tissues have different T1s and T2s. Now, it doesn't mean that a tissue is positively unique, meaning there can be tissues that have very, very similar T1s and T2s, but there's enough differences, for example, between gray matter and white matter, both in T1 and in T2, that we can eke out some important image contrast here and generate images that have white matter, gray matter contrast, for example. Lots of other tissue types have lots of other, of course, have their own T1s and T2s. We'll talk about some of these values as we go. No need to remember specific values for specific tissues. If you work in MR, it'll be important to know a handful of these as reference tissues. And you can, for example, see that something like fat has a pretty short T1 and a kind of intermediate T2, whereas CSF has a really long T1 and a relatively long T2. The thing to remember, probably most importantly, is just the orders of magnitude here. We're talking, hundreds or even 1,000 milliseconds for T1. And we're talking tens up to maybe a couple hundred milliseconds for the T2s. I'm an engineer by training, so orders of magnitude are important. This is the expression that we work through, free precession in the lab frame, or the rotating frame, as it turns out, with relaxation. What happens to the Z component is equally described well in the lab frame and the rotating frame. We worked through it just now in the rotating frame because it's the frame that we'll mostly work in for the rest of the class. We know this first term is that so-called prepared magnetization, and we know that the second term is that return to thermal equilibrium term. When we look at what happens to the bulk magnetization, let's say we take the simple example of this initial condition, this is plotting out those two components of the magnetization. So my initial MZ magnetization might be quite low. How do I generate relatively low MZ magnetization? What do I have to do to my spin system? What if I want my MZ to be 0? What do I do? Force precession by how much? 90 degrees, okay? So this example here is just meant to be, well, let's not make it a 90-degree pulse. Let's make it something less than 90. Maybe it's an 80-degree pulse or a 70-degree pulse. So my bulk magnetization, or my Z magnetization rather, is starting out here. The prepared magnetization, or that mathematical term that represents the prepared magnetization, is going to decay as a function of time. And my MZ magnetization is going to also be driven to return to equilibrium towards M0. And it's the product of that relaxation term and that decay term that gives you the blue curve, which is where the MZ magnetization really starts out and where it eventually really ends up. We don't really separate out those two components in any measurement way. They are terms mathematically. What we observe is just the Z magnetization, if you will. So just showing what those different exponential terms look like. I said this before, but different tissues have different T1s. So when you think about how the magnetization returns to its equilibrium state, it's going to obviously depend on what its underlying T1 is. If all of these tissues, this axis got shifted somehow, if all of these tissues are starting off at 0, for example, then fat's going to recover relatively quickly because it has a short T1. And within about 4 or 5 time constants, it'll be at about 100% of its signal value. Whereas CSF, which has a much longer T1, is going to recover much more slowly. And at the end of 5 seconds, say, it's only recovered about 2 time constants, and it still has more recovery to go. The T1 relaxation is also called the longitudinal or the spin lattice relaxation. It's related to how the individual spins interact with their lattice, the milieu of proteins and other surrounding sort of tissues and molecules, if you will. So it's spins interacting with the lattice of other things. Typically, it's hundreds of milliseconds to maybe tens of milliseconds. Maybe this would probably be like hundreds, even thousands. The T1 increases with increasing B0, so T1's not fixed for a tissue. It's specific for a tissue, but it depends on field strength just slightly. And we can actually decrease the T1 with particular contrast agents. If we have time today, I'll talk a little bit about contrast agents. We can't lengthen the T1, but we can shorten the T1. It's an important thing to remember about the T1. And this will become more meaningful later, but short T1s are bright on T1 weighted images. All the residents, all the fellows always remember this because it's a good governing principle for why is something bright on a T1 weighted image. Short T1s are bright on a T1 weighted image. We haven't gotten to imaging yet. We'll get there shortly, but that's an important thing to remember. We can talk a little bit about when is T1 long and when is T1 short. T1 in general is going to be long for small molecules, things like water, but it's also going to be long for large molecules like proteins. So it has a sort of quadratic behavior, if you will, with regard to the length scale of things. In general, T1 is going to be short for things like fats. Remember, fats have hydrogen in them. They're not bound as water typically, but as CH groups. And it's going to be short for other sort of intermediate-sized molecules. The Bushberg book, which I don't remember if I recommended at the very beginning or not, this is just adapted from that. The students in the physics and biology and medicine track may have this book already. Bottom line, we can get some governing ideas about, what causes T1 to be long and what causes T1 to be short. And if your overall molecular motion is kind of slow, if your molecular size is large, and if your interactions are such that you're relatively bound, then you have a long T1. And we can go over to the other side here and talk about having fast motion and small molecular size and free interactions, and also having long T1s. Now, intuitively, these adjectives, these terms may not mean a whole lot, but if we substitute in particular tissues, it probably makes a little bit more sense. So think of this right-hand side as being cerebrospinal fluid, right? So, So cerebral spinal fluid, it has fast molecular motion. It's really just a fluidic thing after all. It's small in molecular size because it's mostly just ionic water with some small proteins in it. And its molecular interactions are relatively free. The CSF can move around quite easily. This far left-hand column here, I think, stands in for something like muscle. Let's talk about fat because it's the other end of the spectrum, that it's a short T1. So if we think about fats, it's a little hard to say, okay, their molecular motion's intermediate, maybe it's somewhere between something like CSF and muscle. Its molecular size, fats can be relatively big, but they're not big like proteins big. And in terms of how well fats sort of move around and interact with other molecules, maybe you can sort of imagine it's somewhat intermediate relative to something like CSF or something that's really bound like muscle. So again, just trying to give you some intuition as to why these observations have been made and associated with different tissue types. The other component of relaxation is the T2 component. We work through, of course, the solution that describes what happens to the transverse magnetization as a function of time, and it's just a decaying exponential. That state of magnetization is not stable, and as time elapses, then the transverse magnetization just returns to zero. The T2, of course, is different for different tissues, so we can map out decay curves for different tissues like liver, fat, CSF. And we can see that the CSF curve decays relatively slowly because it has a long T2, so it takes a while before the signal's totally decayed, whereas something like liver has a relatively short T2, and that means that the transverse magnetization signal is going to decay pretty quickly, and within, say, 4 or 5 time constants, the liver signal is completely gone. When we think sort of conceptually about what is T2, it's really related to the so-called transverse magnetization, or it's called the transverse relaxation parameter, and it's related to spin-spin interaction. So it's magnetic dipoles interacting with other dipoles. And if you think of these things as being little magnetic bar magnets, they're interacting with each other. It seems natural that they're going to cause each other to point in different directions. They're going to push each other around. They're not exactly attracted. They're pushing each other out of phase. And that leads to signal losses when things fall out of phase. Typically, are on the order of like tens of milliseconds. And T2 is actually relatively independent of B0. So whereas T1 had some B0 dependence, T2 is a little bit more constant. You'll remember this, but it's important that T2 is always less than T1. In the limit, they're actually quite close to each other, but in general, the T2 is usually a fair bit, maybe an order of magnitude less than the T1. As regards image contrast, and it's not obvious yet, we'll talk about this when we get sort of further into the imaging part of this class and signal contrast concepts, but a long T2 is going to be bright on a T2 weighted image. And when we administer contrast agents, there are contrast agents that act on T2 more so than they act on T1. And a T2 contrast agent will decrease the T2. T1 contrast agents, we can shorten the T1. We can also shorten the T2, but we can't lengthen the T1, nor can we lengthen the T2. These are some more sort of just governing principles about when you could sort of expect the T2 to be, greater or smaller. The T2 is going to increase with decreasing molecular size, and it's going to increase with increasing molecular mobility. Again, you may or may not develop some sort of intuition for these things. It's a little easier probably just to build a sense for actual values that correspond to a few sort of key tissue types. And then lastly, the T2 is going to increase with decreasing molecular interactions. We can go back to the same diagram that I've just adapted from the Bushberg book to talk about those same tissues under those sort of same descriptors. And we'll see that the T2 goes from being short for things like muscle, kind of intermediate for things like fat, and being relatively long for things like CSF. And again, these adjectives may or may not give you a little bit of leverage for understanding why the T2 is shorter or longer. We can compare the T1 and the T2 to each other. This is just a plot of the both magnetization's behavior, the Z component of the magnetization and the transverse component of the magnetization. We know that the transverse magnetization component is not stable. It's just going to decay until it reaches a value of 0. And the Z magnetization is going to grow back slowly until it eventually gets back to its equilibrium state, unless it's acted upon by another RF pulse or something like that. This is just showing together how T1 and T2 relate to each other. Again, remember that T1 is always greater than T2. And it's not until, when you get out to some tissues like CSF, for example, here, the CSF, is that still showing? Again, this was the example tissue here was something like CSF that has a pretty long T1 and also a long T2. Scaling's not meant to be precise, just kind of qualitative. Another component, this will be more important when we talk about gradient echoes. There's another relaxation parameter called T2 star. We haven't talked about spin echoes. We haven't talked about gradient echoes. I'll talk a little bit about T2 star relaxation, and we'll talk about it again when we get to gradient echoes, I think. We have this concept of so-called intravoxel spin dephasing. So remember, we have a bunch of spins, right? Avogadro's numbers of spins that populate a pixel or a voxel of interest. And intravoxel spin dephasing refers to the fact that the spins in a voxel may or may not be in alignment or in phase with one another. When we have spin dephasing, it's a consequence of spin-spin dephasing, spins interacting with spins, combined with sources of off-resonance. So if we have an absolutely perfect field across the voxel of interest, it's B0 absolutely at every point, then we only have to, then the signal will only decay because of spin-spin interaction. But it's never quite the case that we have exactly the B0 field within or across even the dimensions of a pixel. And so sources of off-resonance conspire to lead the signal to decay even more quickly. We have so-called B0 inhomogeneity, meaning that the B0 field is not perfect within a single pixel. The pixels are small, right? We're talking little millimeter-sized things. We can also have so-called susceptibility differences. Susceptibility refers to how well the B field, the B0 field, sort of penetrates into the object. And susceptibility differences, whether those are sort of macro scale differences or micro scale, where micro means, sort of protein level and macro means, above the voxel level. These will also cause small field perturbations and therefore dephasing. And we haven't talked about it yet, but we also have so-called chemical shift effects. Different species actually have slightly different resonance frequencies. Fat has a slightly different resonance than water, and all of these things are referred to tetralmethylsilane, which is taken as the NMR standard of being perfectly on resonance. Bottom line, within a pixel, there's no reason that all atomic nuclei should have identically the same precessional frequency. These sources of off-resonance, these three different sources of off-resonance, we'll see later, but they can be rephased with what's called a spin echo. We haven't talked about echoes yet, but we will. We can't recover that lost signal, that signal lost to off-resonance with the so-called gradient echo signal. And it's these sources of off-resonance that conspire to give us an even lower time constant that we call the T2 star time constant, and it's less than our T2 time constant. If we look at it mathematically, we would describe it like this. We'd say that 1 over T2 star equals 1 over T2 plus, and the units work out, but plus gamma times delta B0, some field offset inside of that pixel. Now, I said it, and you may not believe me yet because you haven't seen the math, but these signal losses are in principle reversible. And when they're reversible, then the T2 star just converges down to T2. And I said that these things are reversible when we use a spin echo. They're not reversible when we use a gradient echo. And so sources of off-resonance that show up here cause T2 star to be even lower than the underlying T2 of the tissue of interest. Here's an example of what I mean by, or how we can think about T2 versus T2 star decay. This is great, right? So this is a note. I should have put it in red text, right? This is a note to me after lecture. Back to the slide. I should make a change. I want to update this slide. To do that later this afternoon. The point is that on the left-hand side here, what I'm trying to show is T2 decay. And we have a bunch of bulk magnetization vectors, and they're going to precess in the laboratory frame at the Larmor frequency. That signal can be picked up by my coil, and I'll read out some sinusoidal signal down here. But because of T2 decay, the magnitude of these vectors will also be shrinking, and the magnitude of my signal will also be decaying. So the T2 decay leads to a decay in the magnitude of the signal that I can measure. The time scales don't match, the real Larmor frequency or anything. It's just an example. On the right-hand side, though, I have another problem. I not only have the inherent T2 decay, but I also have spin dephasing, which means my spins fall out of phase with one another, so that at the end of this example here, they're pointing in completely different directions, which causes signal loss. And there's also the underlying T2 decay, which causes signal loss. And so as a consequence of T2 star decay, I've got, in this example, basically no signal after, many revolutions, whereas if it was just T2 decay, I'd still have some available signal. So there's signal loss from spin dephasing, but there's also signal loss, this should just say from T2, sorry, spin dephasing and from T2. This is just an example, probably you get the idea already, of T2 star being less than T2. If I plot out those exponential functions, obviously my T2 star decay curve is going to be smaller. And that just means that if the circumstances are such that my transverse magnetization is governed by T2 star, the signal's not available for as long. It's going to decay pretty quickly. And so just maybe summarizing all of those rules together, then we know that T2 star is less than T2, and that's, of course, going to be less than T1. Let me make a few quick, let me take a peek here at where we are. Yeah, I'll come back to the. Let's just do this really quick. Let's take a couple minutes. I'll give you I'll tell you that MR history thing next time. Okay, so contrast agents. What's the point of a contrast agent? Well, obviously we can administer these contrast agents usually intravenously, needle into the antecubital vein, and we can use this to enhance image contrast in regions that are perfused by the contrast agent. The contrast agent has to be able to get to that tissue, obviously, to have an effect on the MR signal. There's a lot of different kinds of contrast agents. Not all this is critical for this class, but the most common kind of contrast agent used in MR are the so-called gadolinium-based agents. Gadolinium is a heavy metal. It has to be chelated to some other compound because gadolinium by itself is highly toxic. These agents are T1 shortening agents, so they're going to decrease the T1 for tissue compartments that they reach. They're hydrophilic, so they can't cross the blood-brain barrier. And they're blood pool agents that are excreted by the kidneys within a couple hours, and they extravasate into things like tumors and infarcts in your heart across a leaky blood-brain barrier. So because of their molecular size, they can be useful diagnostic tools because we know something about the tissue circumstances if we see, something very, very bright in a region that we don't expect. So if I were to inject a gadolinium-based contrast agent into someone who might have an infarct, that gadolinium-based contrast agent extravasates into the infarct and makes the infarct very, very bright. And it lights up like a bell, and no other technique does it quite as distinctively as MR. These are, in fact, paramagnetic agents. That just means there's some unpaired electrons that increase the susceptibility and increase the local field in such a way that it contributes to shortening the T1, if you will. There are some safety concerns about these agents, but they're very widely used, very broadly used. I can't remember what the numbers is, but it's hundreds of thousands of exams use these agents every year, and they're widely reported as being safe, aside from some typical side effects that may include mild allergic reactions and these kinds of things. There was a scare a few years ago about something called nephrogenic systemic fibrosis. It sounds terrible. It is terrible. It was probably affecting maybe 1 in a few 100,000 patients, and they finally figured out it was a dosing issue combined with a particular agent, and that agent's basically not used anymore. So there's no newly reported cases of this in several years. There are other agents as well. There are the so-called ultra-small paramagnetic iron oxide agents, also T1 shortening agents, also hydrophilic so they don't cross the blood-brain barrier. These are intravascular agents, which is really interesting. That means the kidneys don't excrete them. They stay in your blood pool for very long periods of time and have a half-life of like 14 hours, whereas the gadolinium-based agents have half-lives of, I forget what it was, tens of minutes or hours. These super paramagnetic agents help develop strong internal magnetization to the agent itself. They're largely iron or iron oxide-based agents that have really strong T1 relaxation effects. And there's a lot of research being done here, actually, at UCLA, using furomoxetol to improve our conspicuity for the blood pool, which is a really useful thing diagnostically. If you know where the blood pool is, you know where the vessels are. If you know where the vessels are, you know how the vessels are connected. It's a technique called angiography, and it's really useful for a variety of clinical indications. A little bit there about safety, but these are largely safe agents, typically administered slowly, and sometimes even before the MR exam. Another category of agents not used as commonly as the other two. These are super paramagnetic iron oxide agents. They cause the T2 star to shorten. So the other ones were T1 shortening agents. This is a T2 shortening agent, also hydrophilic, also an intravascular agent, and also super paramagnetic. It's just because of its size that it has a slightly different effect that dominates the T2 star signal more so than the T1 signal. As with any of these agents, there's always a little bit of safety considerations with regard to adverse outcomes or adverse events, but they're typically things like hypertension, low blood pressure, and allergic reactions, mostly very safe agents. When we talk about what a T1 shortening agent does, this is all we mean. If this was the native tissue's T1 recovery curve, this blue curve, as I increase the concentration or increase the dose of the contrast agent, I just get shorter and shorter T1s. And these are just some nice examples of why we might use a contrast agent. This is doing a technique called magnetic resonance angiography. It involves acquiring a 3D image over, say, in this case, the whole chest in like 20 seconds or 25 seconds. And you get these nice images where either through a MIP, a maximum intensity projection, or doing some volume rendering and some software tool called Osirix, you can get these nice, vascular casts, if you will. And so the surgeons really like this because they can pretty immediately say, oh, okay, that's how things are connected for this kid. And the imaging examples are of kids that are, 2 weeks old or 2 days old or 2 years old, very, very young patients with known or suspected congenital abnormalities, meaning that there's some malformation of their major arterial system, and the surgeons want to know what that looks like ahead of time and then think about surgical approaches prior to dealing with that particular patient. So really powerful clinical technique. This is acquired with a T1 weighted image. We added a T1 shortening agent so that wherever the contrast agent is, which is predominantly in the blood pool, we'll get really, really bright signals on a heavily T1 weighted image. There are these T2 shortening agents. We talked about this a little bit already, the SPIO agent being the most common one. Just the example of what this does is that if this is the native T2 relaxation curve, as we're adding or increasing the dose of that contrast agent, we're going to be decreasing the T2, will be causing the T2 signal to decay even faster, causing those particular tissues to be even darker in the presence of the contrast agent. So I know I went through that kind of quickly. You can pick up some of the main details. Mostly what I care about you guys knowing is recognizing that contrast agents can cause a change in the underlying T1 and T2. That's it for today. Maybe if I think we have time when we come back on Wednesday, I'll tell you at least one quick story in MR that I think is kind of fun. Otherwise, I'll see you on Wednesday unless there's questions. Yeah.
Are there any contrast agents that are not administered IV?
I can't be positive. It's a good question. Similar to taking some of the oral iodinated agents for doing for looking at the bowel and the intestines. There may be MR agents that could be used in that way, but it's not done commonly. Okay. Thanks again. See you Wednesday. Your homework assignment will get posted this afternoon. Download it, have a look, and then Wednesday in lecture we can talk about it a little bit. Okay? But look at it ahead of the lecture, otherwise you won't get quite as much out of the discussion.